In the first two sections of Chapter 4, we introduced the concept of discrete probability distributions, and we looked at the characteristics of discrete probability distributions. Then we looked at how to calculate the mean and the standard deviation. Typically, the easiest way to calculate the mean and standard deviation of a discrete probability distribution is to put that information in your calculator and then calculate the one variable statistics. But in the next four sections, we are going to look at four specific types of discrete probability distributions. And each one of these is unique in its definition, and it has a different way of calculating the mean and the standard deviation. The four distributions we are going to look at is first the binomial distribution, then we're going to look at the geometric distribution, then the hypergeometric distribution, and lastly, the Poisson distribution. Of these four distributions, three of them we will be able to do on our calculators. The fourth, the hypergeometric distribution, we will have to use a different method. The TI-84 currently does not have the hypergeometric distribution on the calculator. So we'll have to either use Excel. It's quite easy to use Excel to find the hypergeometric distribution, or we can use a formula, and I'll show you the formula. It's not real difficult to use. First, let's look at the binomial distribution. There are three characteristics of a binomial experiment. Number one, there are a fixed number of trials. So think of trials as repetitions of an experiment. The lowercase letter n is going to denote the number of trials. Two, there are only two possible outcomes in the binomial distribution, called a success and a failure for each trial. The letter lowercase p denotes the probability of a success on one trial, and q denotes the probability of a failure on one trial. So p is the probability of a success, q is the probability of a failure, and the sum of the probability of a success and the probability of a failure will equal 1. The n trials are independent and are repeated using identical conditions. Because the n trials are independent, the outcome of one trial does not help in predicting the outcome of another trial. Another way of saying this is that for each individual trial, the probability P of a success and the probability Q of a failure remain the same. For example, suppose Joe randomly guesses at a true-false statistics question. So Joe's experiment has only two outcomes. If a success is guessing correctly and a failure is guessing incorrectly, then a failure would be guessing incorrectly. So if a success is guessing correctly, a failure would be guessing incorrectly. So suppose Joe in the past has guessed on the true and false questions, and he's seen that historically he gets about 60% of these correct. So Joe always guesses correctly on any statistics true false question with a probability of 0.6. So the probability of a success, P, would be 0.6. The probability of a failure, Q, would then be 0.4. This means that for every true false statistics question Joe answers, his probability of a success, P equals 0.6, and his probability of a failure, Q equals 0.4, remain the same. The outcomes of a binomial experiment fit a binomial probability distribution. The random variable X, remember we describe a random variable in words. The random variable X is the number of successes obtained in the N independent trials. The mean of a binomial distribution can be found by multiplying the number of trials times the probability of a success. The variance can be found by multiplying the number of trials times the probability of a success times the probability of a failure. The standard deviation is the square root of the variance. So the standard deviation may be found by taking the square root of the product in PQ. An individual probability in a binomial distribution may be found using a formula. And here is the formula. The formula uses combinations. That's what that C represents. And a combination is just how many ways out of a total you can take a sample of things. So it's the number of ways you can take a sample. However, our calculator will find binomial probabilities for us. So we don't necessarily need to utilize the formula, especially since we have a calculator that so readily does this for us. Let's look at a couple of examples. The first thing we want to look at is what constitutes a success in a binomial distribution. So let's read this example. Let's determine why it's a binomial, and then let's determine what would constitute a success. The State Health Board is concerned about the amount of fruit available in school lunches. 48% of schools in the state offer fruit in their lunches every day. This implies that 52% do not. What would be a success in this case? Well, a success would be that the school offers fruit. And that's in the lunch every day. So what would be a failure? Well, a failure would be that they don't offer fruit in their lunch every day. Do not offer fruit. So based on the information in this problem, the probability of a success is what? Well, that would be 48% because they're telling us that in this population, 48% of the time the schools offer fruit in their lunches every day. So the probability of a success then would be 0.48. Sorry about the phone ringing in the background there. So the probability of a failure would be 0.52. All right, so let's move on to the next example, and let's demonstrate how you would write a probability question. A trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs the trick is 35%, and the probability that the dolphin does not successfully perform the trick is 65%. Out of 20 attempts, you want to find the probability that the dolphin succeeds 12 times. So state the probability question mathematically. So what are we interested in? what we're interested in, okay, so we know that when we teach this trick to a dolphin, 35% of the time we're successful. The dolphin actually does the trick. 65% of the time we are not successful. So 35% of the time we have a success, 65% of the time we have a failure. So now we're going to look at this dolphin trying this 20 times. And what we want to know is in the 20 trials, what's the probability that the dolphin gets it correctly? It succeeds exactly 12 times. So the probability that we're interested in is the probability that our random variable takes on the value of 12, that the random variables could take on values anywhere between, the dolphin gets it incorrect every time, or one time, or two times, or three times, up to that it gets it correctly 20 times. So what's the probability that it gets it exactly correct 12 times? All right, let's look at this example. A fair coin is flipped 15 times. So the number of trials here is 15. Each flip is independent. What is the probability of getting more than 10 heads? Let X be the number of heads in 15 flips of the fair coin. So what values can X take on? Well, in 15 flips, you could get no heads, or one head, or two heads, or three heads, up to you could conceivably get every flip to be a head, so you could get 15. Since the coin is fair, the probability of a success, or the probability that I actually flip the coin and get a head, is 50%, 0.5. So P is 0.5. And Q would also be 0.5, the probability of a failure, because if I don't get a head, I get a tail. And the probability of getting a tail is also 50%. The number of trials is 15. State the probability question mathematically. So what you're interested in is getting more than 10 heads. What does that mean? Getting more than 10 heads. Well, that would mean that X would either be 11 or 12 or 13 or 14 or 15. So what we're interested in is the probability that X could take on a value greater than 10. So in probability notation, that's the probability that X is greater than 10. So the notation for the binomial distribution is as follows. We use capital B to denote that it is a binomial probability distribution function. And the way we write this is this right here, capital X squiggly line, capital B parenthesis, NP. And this is red. X is a random variable with a binomial distribution. The binomial distribution only has two parameters that affect the distribution. Those two parameters are the number of trials and the probability of a success. So let's do this example. It has been stated that about 41% of adult workers have a high school diploma but do not pursue any further education. If 20 adult workers are randomly selected, find the probability that at most 12 of them have a high school diploma but do not pursue any further education. How many adult workers do you expect to have a high school diploma but do not pursue any further education? So how many adult workers do you expect? So this word right here, the expect, tells us, remember when we found an expected value in section 4.2, we were actually finding a mean. So we are going to have to find the mean of this particular binomial probability distribution. So we're going to let X be the random variable, the number of workers who have a high school diploma but do not pursue any further education. And what probability are we looking for? Well, what we have stated here is at most 12. And whenever you see at most in a mathematical problem, what you're talking about is no more than or less than or equal to. So what we're looking for is the probability that our random variable takes on a value less than or equal to 12. So we're interested in the probability that we could see none, or 1, or 2, or 3, or 4, up to and including 12. So let's write down all the information that we have here. So we're taking a sample of 20 adults. So the sample that we're taking, that is the number of trials. So N is 20. Now we're looking at a probability of success. So we see that in the population, 41% of adult workers have a high school diploma but do not pursue any further education. So if we randomly selected adult from our population, there would be a 41% chance that this person had a high school diploma but does not pursue any further education. So the probability of a success is the 0.41. So the probability of a failure then would be 1 minus 0.41 or 0.59. So this is a binomial probability distribution with 20 trials, and our probability of a success is 0.41. And we're looking for the probability that X takes on values less than or equal to 12. All right, so how do we do this on our calculator? Well, let's just run over to our calculator and let's see if we can't do this. Well, it helps if you go to your calculator. Here we are at our calculator. All right, so on our calculator, we have right to the left of the clear button, we have a button that's labeled VARS. That stands for variables. And above the variables button, we have the DISTR button. That is our probability distributions. So to get to our probability distributions, we're going to hit second, variables. And the first menu here is our distribution menu. And we're going to arrow down through this menu until we find something that looks like binomial. And there they are. So A and B are our two binomial distributions. A is binom PDF. This finds the binomial distribution probability when X takes on an exact value. So this is when X equals something. X equals 12 or 5 or whatever. The second one, B, is binom CDF. This is our cumulative binomial probability distribution. So this is the one we use when we're trying to find the probability when it's less than or equal to. So in our case, since we were trying to find the probability that X is less than or equal to 12, this is what the one we're going to use. So we're going to use B. And I have some information in here. I've already put this in, so you can see what information we have here. The number of trials, since we were taking a sample of 20 people and looking at them, the number of trials was 20. I typed that in and hit enter. The next piece of information that I need to give my calculator is the probability of a success. And we know that 41% of our population has a high school diploma but does not seek education further than that. So that's 0.41. We hit enter. And the value, the X value, the value that our random variable is going to take on is 12. And since we're using the cumulative binomial distribution, this is going to find the probability that X is less than or equal to 12. So I'm going to hit enter one more time. And the last piece of information in this window is the paste name, the paste word. And when you click enter on paste, it actually pastes the binomial distribution back into your home screen. So if you don't have that menu where you can put in the number of trials and the probability of a success and X, then what you would have is the binom CDF, open parentheses, and then you would type in the information. So the first number here, the 20, is the number of trials. You're going to then put a comma. The next number you put in is the probability of a success, 0.41, then type in a comma. And the last number you type in is the value of your random variable. Close your parentheses and hit enter. So what we see is that the probability that our random variable takes on a value less than or equal to 12 is 0.9738. So a very high probability that our random variable will take on a value less than or equal to 12. So here on this slide are the instructions for doing this. Second distribution. The syntax for the instructions are as follows. If you're finding the probability that X equals a value, you're going to use binom PDF. The first number you put in is the number of trials. The second number is the probability of a success. And the third number is the value that your random variable takes on. If the number is left out, then it creates a binomial probability table. If you're interested in finding the probability that your random variable takes on a value less than or equal to some number, then you're going to use the binom CDF. And again, the first number is the number of trials. The second number is the probability of a success. And the third value is the number that your random variable takes on. Again, if the number is left out, then it creates a table for you. Okay. If you wanted to find the probability that you get exactly 12 people in this sample of 20 who say they have a high school diploma and no education beyond that, you would use binom PDF. You'd put 20.41 and 12, and that probability would be 0.0417. Now, if you're interested in finding the probability greater than 12, so what's the probability that we get more than 12 people who say they have a high school diploma, but they don't have any education beyond that, then what you have to do is take the binom CDF at 12 and subtract that from 1. So the probability that X is greater than 12 is 1 minus the probability that X is less than or equal to 12. And in this case, that would be 0.02622. Now the graph of the binomial distribution looks like this. This is the binomial distribution with 20 trials and a probability of a success being 0.41. In this graph, the y-axis contains the probability that x takes on a particular value. So for example, if you look at this graph and you look at, say, x equals 3, it looks like the probability is about 0.025 for x to take on the value of 3. I think that was 2, not 3, 2. Looks like 3 is about I don't know, 0.06, something like that. The number of adult workers that you would expect to have a high school diploma but not pursue any further education is the mean. And the mean can be determined in a binomial distribution by taking the number of trials and multiplying that times the probability of a success. So you would expect in this sample of 20 to see 8.2 people who have a high school diploma but not any further education. Of course, that's not necessarily true for every trial of 20. Sometimes you might see more, sometimes you might see less, but on average, you would expect to see approximately 8 people saying they have a high school diploma but not any further education. To find the standard deviation, you multiply the number of trials times the probability of a success times the probability of a failure, and you take the square root. So the standard deviation for this particular binomial probability distribution with 20 trials and the probability of a success being 0.41 is 2.20. Let's look at this example here. About 32% of students participate in a community volunteer program outside of school. If 30 students are selected at random, find the probability that at most 14 of them participate in a community volunteer program outside of school. And we are going to use our calculators to find this value. So what we're interested in is at most 14. So that means less than or equal to 14. So we're interested in the probability that x takes on a value less than or equal to 14. So now let's write our binomial distribution. So this is binomial. We have 30 students that we're looking at. So the number of trials is 30. The probability of a success is 32%. So P is 0.32 because 32% of our students participate in a community volunteer program. So Q would be 0.68, although we're not going to use Q in this particular example because we're not finding the standard deviation, but it's kind of nice to know what that is. Okay, so what we need to do is we need to go to our calculator, and this is going to be a cumulative. So we're going to use a binom CDF, and we're going to put in that our trials are 30, our probability of a success is 0.32, and we're going to look at x is less than or equal to 14. So that's what we need to put into our calculator to calculate this probability. So let's go to our calculator. All right, so we're going to go to our distribution. We're going to find our binomial CDF, binom CDF. The number of trials, we were looking at 30 students. Probability of a success was 0.32. 32% of these kids participate in a community volunteer program. And we're interested, what's the probability that if we randomly select 30 students that x will take on a value less than or equal to 14. So 0, 1, 2, 3, 4, 5, 6, up to 14. Okay, so calculate, and we get 0.9695. All right, let's look at another example. In the 2013 Jerry's Artorama Art Supplies catalog, there are 560 pages. 8 of the pages feature signature artists. Suppose we randomly sample 100 pages. Let X, the random variable, be the number of pages that feature signature artists. What values does our random variable take on? And what is the probability distribution? Well, what values would X take on? Well, if we randomly selected 100 pages from this catalog of 560 pages, we could potentially not see any pages that featured a signature artist. Or we could see 1, or maybe 2, or 3, or 4, or 5, or 6, or 7, or 8. We're not going to see more than 8 pages in this sample of 100 because we only have 8 pages in the catalog that have feature signature artist. So our random variable could take on values from 0 to 8. And this is a binomial because when I look at these 100 pages, the page either has it either features a signature artist or it doesn't. It does one or the other. So we have a success or we have a failure. A success would be that it does feature a signature artist. A failure would be that the page doesn't. So this is binomial. And we're looking at 100 pages. So our number of trials, N, is 100. And what's the probability of a success? Well, if I have a catalog that contains 560 pages and 8 of those feature signature artists, then the number of outcomes, successful outcomes, would be 8 pages out of 560. So our probability of a success would be 8 over 560. So now let's calculate some probabilities. Let's find the probability that 2 pages, exactly 2 pages, feature the signature artist. So this would be the probability that X is exactly 2. So how would we do that? Well, we would use our calculator and we would use a binom PDF because we're looking for that the random variable takes on an exact value, not anything greater than or less than, but exactly 2. So we would go to binom PDF. The number of trials is 100, and the probability of a success is 8 over 560. And we're interested in exactly 2 of these pages of the 100 that we sample contain a featured signature artist. So let's run over to our calculator real quick and let's do this on our calculator. The other 2, I'm just going to write the instructions down and I'll let you do those on your calculator later. Okay, so I'm going to go to my binom distribution and I want the PDF, so that is A. The number of trials, well, there are 100 pages that we're looking at. And I'm going to type in P as a fraction, and my calculator will calculate that for me. So 8 divided by 560. And when I hit enter, I go to the X value and I'm going to type in 2. Now I'm going to hit enter again, and then I'm going to go paste this back into my home screen. And I get 0.2466. So you see, I didn't actually have to do the probability calculation before I put it in my binomial distribution. My calculator can do that for me. So this was equal to 0.2466. So the second part of this, part B, we want the probability that at most 6 pages feature signature artists. So at most, remember, is less than or equal to. So we're interested in the probability that x is less than or equal to 6. So now we're going to use the cumulative binomial. And again, we have 100 trials. The probability of a success is 8 over 560. And we're interested in our random variable taking on a value less than or equal to 6. And my calculator says that this is 0.9994. The last probability that we're going to calculate is more than 3 pages. So this would be 4, 5, 6, 7, or 8 pages. So we're interested in the probability that x is greater than 3 or 4 or 5 or 6 or 7. So how do we do this? Well, to do this, we're going to find 1 minus the probability that x is less than or equal to 3. So if we look at probability, if we find the probability that x is less than or equal to 3, we get a value. If we subtract that from 1, that should give us the probability that x is greater than 3. So we're going to find this by finding 1 minus the probability that x is less than or equal to 3. So in our calculator, we'd say 1 minus the binom CDF. And now we're going to have 100, 8 over 560, and 3. So when we do that calculation on our calculator, we get 0.0557. Okay, using the formulas, calculate the mean and the standard deviation. To calculate the mean of a binomial distribution, we take the number of trials and we multiply it by the probability of a success. So that would be 100. We're looking at 100 pages times the probability of a success, which is 8 over 560. And I did this on my calculator and I get approximately 1.4286. What's the standard deviation? Well, sigma is the square root of NPQ. And I know that N is 100, P is 8 over 560. And then what's Q? Well, if P is 8 over 560, Q would be 1 minus 8 over 560. So that would be 552 over 560. All right, taking my calculator out, when I calculate 100 times 8 over 560 times 552 over 560, I actually do not have that written on my paper, on my note sheet, but I'm going to let you do that calculation on your calculator, whatever that is. Hopefully, oh, there it is. I have it on the actual slide. So that's 1.1867. Don't have it in my notes, but I do have it on the slide. And that is the end of section 4.3. We'll continue in the next video looking at the geometric distribution. Then we'll have another video, the third video, where we'll cover both the hypergeometric and the Poisson.